Welcome back to Calculus 1. Today, we are deep diving into one of the most critical visual skills you will develop in this course, reading and estimating limits directly from a graph. In calculus, the graph is your most powerful intuitive tool. We aren't just scanning the axes to see where a single point sits, we are studying the dynamic, continuous path that the function takes as it approaches that specific x value. Remember this fundamental rule. The value of the function exactly at a point, denoted as f of a, is often completely irrelevant to the limit itself. We only care about the intended height or target value that the function is aiming for from both the left and right sides. To rigorously analyze these complex points, we split our approach into two distinct directional paths. First, the left-hand limit, written with a negative superscript, tracks the function's height as x approaches from values smaller than our target. Second, the right-hand limit, written with a positive superscript, tracks the approach from values larger than our target. For a standard two-sided limit to exist, these two independent paths must align perfectly and converge at exactly the same height. If they don't, the two-sided limit definitively does not exist. Let's apply this to example 1, where we encounter what is formally known as a jump discontinuity at the x value of 3. Notice that the graph is broken into two distinct horizontal segments. First, let's analyze the left-hand approach. As we trace the blue line moving from left to right, getting infinitesimally close to x equals 3, the function remains perfectly flat at a y value of 2. Therefore, we state that the left-hand limit is exactly 2. Now, let's shift our focus to the right-hand approach. As we trace the path moving from right to left toward x equals 3, the function operates on a completely different level, hovering consistently at a y value of 4. Therefore, the right-hand limit is exactly 4. Now we compare the two results. Since the left-hand limit of 2 is clearly not equal to the right-hand limit of 4, the paths do not meet. Consequently, the general two-sided limit at x equals 3 does not exist. The vertical gap between these two heights creates an unbridgeable disconnect in the limit's logic, a classic hallmark of a jump discontinuity. Moving to example 2, we encounter a more subtle scenario, a removable discontinuity, visually represented as a hole in the graph at x equals 1. If you look closely at the grid, the actual defined point for the function, f of 1, is located way up high, represented by the solid dot at a y value of 5. However, remember our golden rule. Limits do not care about the destination point itself, they only care about the journey. Let's activate our tracers. As we ride the curve from the left side, approaching an x value of 1, the y value of the curve smoothly slides down, aiming precisely at a height of 2. Now, let's ride the curve from the right side. As we approach x equals 1 from values greater than 1, the y value slides up along the curve, again aiming precisely at that very same height of 2. Because both the left-sided approach and the right-sided approach agree perfectly and point to a y value of 2, we conclude mathematically that the two-sided limit exists and is exactly equal to 2. The function is defined at 5, but its limit is 2. This example reinforces the core principle of calculus. The limit evaluates the trend, not the isolated point value. For example 4, let us examine a scenario involving infinite limits. Here we see a rational function graphed and a distinct vertical dashed line at x equals 0. This is a vertical asymptote. Watch what happens to the function values as our x-coordinates get closer and closer to 0 from either direction. Let's trace from the left first. As x approaches 0 from the negative side, the graph accelerates upwards, unbound, growing larger and larger without ever stopping. The I values shoot toward positive infinity. Similarly, if we trace from the right side as x approaches 0 from the positive values, the graph again sharply curves upwards, mirroring the left side and shooting infinitely high. Because the function's values grow without bound in the positive direction from both sides, we categorize this behavior mathematically. We say the limit as x approaches 0 is positive infinity. It's crucial to understand that infinity is not a standard number, but rather a descriptor of boundless behavior. This represents a specific classification of a limit not existing in the traditional numeric sense, but rather existing conceptually as infinite growth. Note well, if one side had gone to positive infinity and the other to negative infinity, we would simply declare that the limit does not exist at all without assigning an infinite direction. Finally, let's push into a truly advanced university-level scenario with example 4, the oscillating discontinuity. Look closely at the graph of this trigonometric function as we zoom in on the origin, x equals 0. As our x values get smaller and smaller, moving toward 0 from either side, watch the frequency of the waves. The function vibrates up and down between y equals -1 and y equals +1. But here is the critical part. As we get closer to 0, the oscillations become incredibly rapid, vibrating infinitely fast. The function never settles down or aims at one single stable y value. No matter how infinitesimally close we zoom in, the y value jumps wildly between 1 and -1. Because there is no single target height that the function is approaching, the limit fundamentally fails to exist. You simply cannot predict where the graph will be. This example is vital because it proves that a limit requires stability and a clear target. Mastering these visual cues, jumps, holes, asymptotes, and oscillations is the absolute foundation for everything we will do with limits and continuity moving forward in this course.